Welcome to the deep dive. Today we are taking a fascinating and really foundational journey into the structure and behavior of matter.
That's right, we're going right to the core of chemistry.
We're tackling the full landscape of the states of matter.
Our mission today is to distill an entire chapter, the principles of gases, the transitions of liquids, and, crucially, the four major solid structures.
All to give you a crystal clear understanding of how bonding dictates, well, everything, from melting point to electrical conductivity.
And we're going to give you that clear understanding.
And before we get into the familiar territories of solid, liquid, and gas, we have to start with something a bit stranger, a concept that proves matter can be far more complex.
The fourth state liquid crystals.
Right.
Think about this. When you heat a specific compound, like cholesteryl benzoate, it melts from a solid at 147 degrees Celsius. But it doesn't immediately become a clear liquid.
No, it forms this cloudy, sort of opaque liquid first.
Exactly. It only becomes truly transparent when it hits 180 degrees.
That cloudy state in between is the liquid crystal metaphase, and it's wild. The molecules, which are typically rod-shaped, have lost their perfect fixed structure, but they haven't lost all structure.
Right, they can move, but they still point in roughly the same direction.
And this partial directed alignment is the key, isn't it?
It is. Because the molecules are rod-shaped and partially organized, applying just a tiny electrical field can rotate their structure.
And that rotation lets them block or transmit light.
Precisely. That's how you create the pixels that make up every liquid crystal display or LCD screen you look at.
It's amazing that partial structure fundamentally changes its function. And that brings us back to the classic definitions we use to classify states.
In terms of particle proximity, arrangement, and motion.
Yeah.
So for gases, the particles are really far apart, they're randomly arranged, and they move completely freely. That makes them highly compressible.
No fixed volume at all. Then you have liquids.
Right, they're close together, have a fixed volume, but the arrangement is mostly random. That allows for limited movement, which is why they flow and take the container's shape.
And finally, solids. The particles are touching, usually in a very regular arrangement, and they can only vibrate in fixed positions.
Which is why they have a fixed shape and volume and are, for all practical purposes, incompressible.
Okay, so the state a substance exists in is ultimately governed by its internal architecture.
And throughout the rest of our discussion, you should keep in mind the four primary structural types we'll be analyzing.
Simple molecular, giant ionic.
Giant metallic and giant molecular, which is also called covalent.
Okay, let's move on to the gaseous state and the kinetic theory of gases. This theory is basically built on the idea that gas molecules are in constant, random, rapid motion.
It is, and to make the math work, we have to define what we call an ideal gas. This is based on 5 assumptions, but 2 are really crucial for understanding real chemistry.
What's the first one?
First, the distance between molecules is so vast that the volume of the molecules themselves is, well, it's negligible.
We treat them as if they take up zero space.
Exactly, zero space. And the second key assumption, that there are absolutely no intermolecular forces of attraction or repulsion between them.
So they just fly around and bounce off each other with no energy lost.
Right, the collisions are perfectly elastic, and the temperature relates directly to their average kinetic energy.
Okay, so if they are moving so fast and randomly, what is pressure, chemically speaking?
Pressure is simply the cumulative result of all those gas molecules colliding over and over with the inner walls of their container.
So more frequent or more energetic collisions mean higher pressure?
Precisely. And this theory gives us our core mathematical relationships. Volume is inversely proportional to pressure if you hold temperature steady.
And volume is proportional to temperature.
Provided the temperature is measured in Kelvin. You must always convert Celsius by adding 273. Always.
And we combine all this into the cornerstone equation of gas chemistry.
The ideal gas equation. PV equals nRT day.
And this is where you have to be absolutely militant about the units, or the answer is just, it's nonsense.
It really is. P, pressure, must be in pascals per meter. Volume must be in cubic meters, m cubed.
Yeah.
And T, temperature, has to be in Kelvin.
N is your moles, and R is the gas constant, 8.31.
Get any of those wrong, and your calculation will fail.
But this equation is invaluable. It lets you calculate pretty much anything. Volume, pressure, moles, even the relative molecular mass, the molecular element of an unknown substance.
That's right. Say you need to find pressure, and you're given a mass in grams. Your very first step has to be converting that mass into moles.
And make sure your volume is in cubic meters, not decimeters or centimeters cubed.
Right. The utility is tremendous, even if determining the story of a light gas in a lab is practically difficult. Buoyancy messes with the weighing.
Okay, let's unpack this. Despite its utility, the ideal gas law has its limitations. Real gases, they deviate.
They do, and they deviate most significantly under two conditions: very high pressures and very low temperatures.
Why do those extremes break the ideal model?
Well, under high pressure, you're forcing the molecules closer and closer together. Suddenly, the tiny volume of the molecules themselves is not negligible compared to the container space.
Ah, so that first assumption breaks down.
It does. And at very low temperatures, the molecules are moving so slowly that those intermolecular forces we assumed were zero.
The van der Waals forces.
Exactly. Those instantaneous dipole-induced dipole forces. They suddenly become significant enough to have an effect.
And when those attractive forces kick in, what happens to the measurement?
They pull the molecules toward each other and away from the container walls. This reduces the frequency of collisions.
Meaning the pressure you actually measure in the lab is lower than what the ideal gas equation predicted.
Precisely. The model fails when those two key assumptions fail.
Okay, let's move on. Next state in the process of thermal change, the liquid state and phase transitions.
So when you heat a solid, the particles vibrate more and more vigorously until, at the melting point, they gain enough energy to start sliding past each other.
And structure is key here.
Absolutely. Simple molecular solids melt easily. You only need to overcome weak intermolecular forces. But ionic solids, they require massive amounts of energy because you have to break those incredibly strong ionic bonds holding the entire lattice together.
Okay, so that's melting. What about vaporization?
Vaporization is the change from liquid to gas, and it includes two processes. First is evaporation, which can happen below the boiling point. It's just the fastest particles at the surface escaping.
And then there's boiling.
Right, which happens only at the boiling point when all the particles have enough energy to break free entirely. The energy required to do this for 1 mole is the enthalpy change of vaporization.
What happens if you do this in a sealed container?
Then you establish a dynamic vapor pressure and equilibrium. At first, molecules escape as vapor. But pretty soon, those vapor molecules start losing energy and condensing back into the liquid.
So it's a two-way street.
Exactly. And equilibrium is reached when the rate of escape equals the rate of return. At that point, the concentration of vapor stays constant.
And the pressure exerted by that vapor is the vapor pressure.
Yes, and this directly defines the boiling point. It's the temperature at which the liquid's vapor pressure finally equals the atmospheric pressure pushing down on it.
1 atmosphere, or 101,325 pascals.
Now let's transition entirely to the solid state, which is defined by that highly organized crystal lattice.
The regularly repeating arrangement of ions, atoms, or molecules. This is where those structural types we mentioned earlier determine everything you experience about a material.
Starting with giant ionic structures like table salt, sodium chloride.
Right, it's a massive 3D arrangement of alternating positive and negative ions.
And they're locked in place by incredibly strong electrostatic forces acting in all directions.
Because those bonds are so strong, they have extremely high melting and boiling points, and they're very hard.
But here's the interesting paradox. They are also brittle.
Why is that?
If you hit an ionic crystal, the layers can shift just slightly. And when they do, ions of the same charge suddenly line up next to each other.
Which would cause massive repulsion.
Massive repulsion. And the crystal just cleaves. It splits right open.
And what about conductivity?
It's strictly limited. Ionic compounds only conduct electricity when they are molten or in solution because the ions need to be mobile to carry the charge.
Can you give us an example of how much the bond strength matters?
A great one is comparing sodium chloride, NaCl, to magnesium oxide, MgO. The melting point of salt is about 801 degrees Celsius. For MgO, it's 852 degrees.
Whoa, that's a huge difference.
It's fascinating, and it's all due to charge density. In MgO, you have a 2 plus and a 2 minus ion. That doubly charged attraction is exponentially stronger, requiring far more energy to break.
Incredible. Okay, our second type, giant metallic structures.
Like copper or iron. You can picture these as a lattice of positive metal ions sitting in a vast, mobile sea of delocalized electrons.
And that mobile electron sea is the chemical secret to all their properties.
It really is. It explains why they conduct electricity perfectly, whether they're solid or liquid. And it also explains why metals are so malleable and ductile. When you hit a metal, the layers of positive ions slide over each other. But that flexible electron sea just flows around and reforms the metallic bond in the new position.
So it doesn't shatter like an ionic compound.
Never. And that's also why alloys are usually stronger. If you add a different size ion, like zinc into copper to make brass, you disrupt that perfect regular lattice.
Which makes it harder for the layers to slide.
Much harder, so the material becomes stronger, but often a bit less malleable.
Next up, simple molecular lattices.
Things like iodine or dry ice. Here, you have strong covalent bonds within each molecule, but between the molecules, there are only weak intermolecular forces.
And that contrast defines their properties.
Completely. They have extremely low melting and sublimation points because you only need a tiny bit of energy to overcome those weak forces and break the lattice apart.
Finally, we get to the chemical fortresses, giant molecular or covalent structures.
Yes, substances like diamond, graphite, silicon dioxide. They're defined by a massive three-dimensional network of strong covalent bonds extending through the entire structure.
Which means one thing, extremely high melting points.
Extremely high. Let's compare the allotropes of carbon. Diamond is a tetrahedral network where every carbon forms 4 strong covalent bonds.
It's the hardest natural substance, has a massive melting point, but it's a non-conductor. All its valence electrons are locked up in those bonds.
Right. Now, graphite is structurally different. It's made of planar layers of hexagons, with each carbon bonding to only 3 neighbors.
And that fourth electron from each atom.
It forms a cloud of delocalized electrons above and below the layers.
So because of the weak forces between the layers, graphite is soft and slippery.
But because of those mobile delocalized electrons, it is an excellent conductor of electricity, specifically along the layers.
Right, what about the more high-tech carbon structures, the fullerenes?
Right, you have buckminsterfullerene C60. It's a simple molecular structure shaped like a tiny football. That means it has a relatively low sublimation point and is a poor conductor. It just doesn't have that extensive delocalization of graphite,
And then you have nanotubes.
which are essentially rolled up sheets of carbon hexagons. They're unbelievably strong, up to 100 times stronger than steel, and have very high electrical conductivity along their length.
And finally, graphene.
A single isolated layer of graphite. It's the most chemically reactive form of carbon, incredibly strong for its mass, and conducts electricity and heat even better than graphite itself.
So if we synthesize everything we've covered, from the chaotic movement of ideal gases to the stability of crystalline solids, the biggest lesson is this. A substance's properties are determined entirely by how its parts are bonded together.
That's the key takeaway. A final recap. Strong bonds and giant structures, ionic, metallic, giant, molecular mean high melting points. Electrical conductivity requires mobile charge carriers.
Either delocalized electrons, like in metals and graphite, or mobile ions, like in molten ionic compounds.
And simple molecular structures are weak and melt easily because only those weak intermolecular forces need to be broken.
Thank you for joining us for this deep dive into the structure and properties of matter. We hope this has given you the conceptual tools needed to analyze the behavior of any substance just by looking at its structure.
And as you reflect on the high-tech examples of carbon we just discussed, nanotubes and graphene, consider this provocative thought. Since these structures rely on being extremely thin, elongated, and highly conductive layers of atoms, how might scientists leverage these unique features to create materials that are both incredibly strong and optically transparent, paving the way for truly revolutionary flexible display technology?